Okay, good morning. I guess we can begin our session today. I want to introduce myself. My name is URAL. I'm the Vice President of the Istanbul Technical University and Professor of Civil Engineering. Perhaps more importantly, I'm the Secretary of the International Association for Housing Science, for IHS. And it's wonderful to be here today with you. We have 6 presentations that are confirmed, and we have 3 that perhaps might walk in a little later, 4 that might walk in later. And according to the schedule, we have 1 minor change. We will have the paper number 955, entitled Proposal for Optical Method of Quality Control of the Surface of the Slabs of Natural Stone for Cladding Facades by Professor Zamora Mestre will be first. So please, Professor.
Thank you for your attention. Dear colleagues, Chairman, Mr. URAL, I will communicate to you about our work in last year, about a proposal, it's only a proposal at this moment, for an optical method of quality control of the surface, quality surface of course, of the slabs of natural stone for cladding buildings facades, applied in situ. I think that this is the most focus we are, to find new techniques to apply in situ, because we have not the usually resources that we have at the laboratory or with computers. The summary of this presentation will make this way. First of all, an introduction, the technical references that we have at this moment on our mandatories, measurement of the surface station of the concrete, the stone cladding that we study, description of the technique applied for recognition, types of defects initially detected, photographic map of the defects detected looking at the PC screen, statistics results, and after conclusions. First of all, just a little introduction. When we find as technical the existence of a significant number of surface defects in concrete stone cladding of some building facades, we must to proceed first of all to locate these defects in the surface facade. That means to map, and it's not many times it's very difficult to map because you must access to many parts of the building that maybe are inaccessible. To classify these defects according to a typology, you can see on the next slides that the fashionable classification is maybe in a way on a factory defects, but not in a building site defects. And finally, to quantify the number of defects by type and also but per unit area. No, at this moment maybe we have no disasters, because we are good professionals maybe, but we have a lot of little disasters, but are distributed on the surface on our buildings in a way that we must know it statistical, because it will depend on the intensity of these diseases. To answer these questions, it usually suggests to use the following standard methodology. Here you can see our technical reference in Spain is the Spanish norm, UNE, and 1469, natural stone products, slabs for cladding, requirements. And where this norm talks us about the visual appearance, because I visual defects, you can see here a young man, he's a pretty good man, you say, maybe sympathetic. You can see a window. I think this is an old-fashioned way to recognize the surface defects, and that are comparing in the same way, maybe with a coffee, with a radio, comparing all the day a quality supposed surface with a unquality supposed not surface. I think this is a good system maybe in the 19th or maybe in the 20th century, but it's not applied at the building site and not at this moment when everybody has another kind of resources, then we can apply other techniques. But I was surprised that there was not, or I can find any other resources. And even when you read these norms, you can see it's permissible any visible changes such as cracks. What is a crack exactly? Inclusions, cavities, steolitas, veins, as they are typical of the stone. What does it mean, typical of the stone? Well, we tried to do this. First of all, this is the building we should study. And we made some measurement of the surface station of the stone cladding. It was is a sandstone from Alicante. The local name is Batej. It's a good sandstone. People likes very much this sandstone because of this appearance. because it's not a very strength stone. It's not for building. It's only for cladding, we say. Then does it mean that the surface quality must be 5 stars, the maximum quality, because we pay for this appearance. We don't pay for the qualities of absorption, humidity, and other questions. Description of the proposal technique we apply for this recognition. We have proceeded to photograph each of these facades with a digital photographic camera, a Nikon Coolpix. Maybe you have one like this, 12 megapixels. But maybe 2 years ago it was difficult, but now it's easier to find a camera like this, resolution, a normal program exposure, an ISO speed index 64. Later, these images have been treated with a specific image processing software to correct curvature of the lens. You have the first problem. Imagine you are at the street level, but you can access to the up of the building, and then you can use maybe all the techniques, vertical works, or you need a crane. We must use usually resources. As the visualization of the surface defects of the stone through photography depends on the conditions of environment lighting, because it all depends on at what time, in the morning, in the afternoon, the facades may be oriented to the north and the south, the pictures are not the same, of course. This is artistic photography, you know. At the time we take, we must do a little process to homogenize this information in order to make an objective campaign. This homogenization is simple, that we propose. Of course, maybe in the future we can improve it. It consists in modifying the initial parameters, you know, the usually software we can access that for improving images has all the same, Photoshop, CorelDRAW, another thing like this, have always the possibility to modify the brightness on the contrast of these images. It's very easy. Maybe it's a system of error to prove. It is not as only a law. Phase to achieve a comparable image that manifests as possible the existing surface discontinuities for their identification on the screen of the computer. Here you can see a lot of these pictures divided in 3 groups. On the left side you can see the original pictures, one from the north, another from the south. You can see there are differences. You can see the difficulty to take pictures from the street level. And on the second pillar of photograph you can see the correction with the lens. There are software very easy to find on the internet that you can correct this distortion. For our purpose, it's not a big problem. And on the right side, you can see transform this color only on a gray scale. Finally, we decided to transform in a gray scale because we think that in that case of this stone, sandstone, is enough the gray scale. The photograph that we take in the suit orientation, we change the parameters of brightness and contrast for 60 to 14. And for photos taken on the north orientation, we find that it was sufficient enough to modify the contrast to 70 to 30. Subsequently, images were desaturated to achieve maximum uniformity among all fronts. Okay, here you can see the types of the defects, where notches, fluorescence, scratches, broken, coral contamination, slabs that were repaired, and we can see that were transformed, marks, maybe warehouses. When the sun is at the sandstone has warehouses, there are problems or changes of color because of the way they storage. And here we transform every one of these diseases in a dot of color, and every one. And we put all these dots of color, and that's the part of our process that is not automatic. We need a people like the old norm looking at the PC screen. Then was putting all this, you can see the transform of the first photograph to the last photograph, putting these little color dots on the image as I see on grayscale. And with this simple method, you can easily detect on every of these dwellings, every of these diseases or anomalies to make a count. I think this is the part of the process that in the future can be automated. It's not very difficult to make an automatic process with our computer and make an easy account. We found it 620 diseases, that anomalies, little defects. But the most one in this case were scratches and also they repair it. That was that the contractor also found there were a lot of them and he tried to repair, but the reparation was worse than the original defect. Well, conclusions, I think. The technique applied in this case has proven to be able to answer the initially technical questions. Precise location of the defects. We have a map. Classification of these defects that are different because our defects on the factory are not the same that defects on the factory in the building site. Quantification on the number of defects per unit area. That is very interesting to know how is the intensity of this affectation. And also it can be concluded. This method is affordable. I think that at this moment we need affordable methods. It's simple, it's fast, and also it can be improved in the future, maybe with your suggestions. Maybe we can, I think it's, we can make a trip with this method. And the final result presented in the way of photographic maps facilitates an easy access to information for managers, technicians, lawyers, consumers, etc., not only for professionals. It's important to share the quality of information that everybody has the same information. Thank you very much for your attention.
Thank you, Professor Zamora, for also keeping within the time limits. Since Professor Zamora has to leave early, if there are any questions for him, perhaps we can take a question now. I think that your presentation was very clear, and it's a very good proposal since it's affordable and time efficient, and perhaps in the future using artificial intelligence tools can also be an option.
I think the next step will be to make some automatic.
Yes.
Here was maybe, I think it's 2,000 meters of sandstone. It
Yes.
would be 20.
Sure, then you would
it will be difficult for a person that's looking all day to the big screen.
Sure.
And I think there is a lot of software we try it to do recon an easier way.
Thank you very much. We can move on to our second presentation. The presentation is entitled Early Age Concrete Temperature and Shrinkage Monitoring by Using Fiber Bragg Gratings by Ignacio Paya Zaforteza.
Okay. Thank you, Mrs. Chairman. Good morning, ladies and gentlemen. Thank you for coming to the presentation with this sunny and very nice day outside. My name is Ignacio Paya Zaforteza and I come from the Technical University of Valencia from the School of Civil Engineering. And I will do this presentation of this paper that deals with some fiber optic sensor that we have developed to measure early age properties in concrete. So I think that we all know that long-term behavior of concrete is heavily influenced by what happens during early ages. And specifically, it is very important to take into account shrinkage strains and also temperature changes because they can produce early age cracking. And this early age cracking can produce some attacks to both concrete and reinforcing bars. And these attacks can enable some noxious substances to come into the concrete and they will produce some damage to both concrete and reinforcing bars. And this will produce at the end a decrease of the durability of the structural element. But if we perform some kind of monitoring, then we can detect damage on time and then we can implement some kind of corrective action and we can, with just small investments of money, we can increase greatly the lifespan of the structure. And this kind of monitoring can be done by several techniques. Traditionally, it has been done with electrical or conventional electrical sensors, but nowadays we are using more and more fiber optics. This is due because fiber optics has some advantages. For example, one of the most important one is what we call multiplexity. That means that with just one fiber you can place many sensors in just one fiber. So in the construction site you will have just one cable and you will not have one cable for each one of the electrical sensors that you are using. And it is also important that nowadays the cost of the optical fibers it is decreasing more and more. And then within this general context, the main goal of this talk was to show two sensors, the process of validation of these two sensors that we have developed, and also to show one application of one of these sensors to a real work site. These sensors are based on what we call the fiber Bragg grating technology, And they have been developed at the Universidad Politécnica de Valencia by two institutes. One of them is ICITEC. I belong to ICITEC and to the School of Civil Engineering, and we are specialists in structural engineering and specifically in concrete. And the second institute is ITEAM, and they are specialists in telecommunications, so it is a multidisciplinary team. Unfortunately, these sensors are in process of being patented, and I cannot give the details of the sensor, but I can give just a sort of overview of what is an optical fiber. So you can see a 3D view of an optical, of an optical fiber here, and in these sensors are based on measuring the changes in the properties of the light that is traveling through the core of the optical fiber, and then there are some kind of algorithms that transform these changes in the light properties into the properties that we want to measure. This property can be strains, it can be temperature, it can be humidity, pH. There are many possibilities. And in any optical fiber, we always have a core, that is this part, that is a thin glass fiber, and the light is traveling through this thin glass fiber. Then we have what we call the cladding, that is this part, and then this is made to confine the light within the core. And finally, we have a jacket, an external layer, that is done to protect the fiber and also to give the fiber mechanical strength. And then I will speak now about how we have checked the behavior of our sensors. First of all, I will speak about the shrinkage sensor and then about the temperature sensor. Then to check our shrinkage sensor, we have used what we call the photogrammetry techniques. So you can see we made 3 specimens of concrete, prismatic specimens. You can see them here. And then we measure shrinkage by taking pictures with this camera and by making some processing of the images taken with the camera. And then these are the results that we obtain. And then we also we place some of our sensors here, and we measure the strain due to shrinkage that we obtain with this orange line that you can see there. So there is a very good agreement between 2 methods. What happens is that our sensor is only able to work after 3 hours, after 3 hours after pouring, so you cannot measure shrinkage since the early beginning. But in any case, this is a big advantage because conventional sensors, they can measure shrinkage after 24 hours. So we are having a very good improvement. And also it is important to notice that usually the shrinkage is not important during the first 3 hours. In this case,
Yes, Professor Paez Fortes, I think we need to congratulate you for your efforts. It's really exciting to see the use of fiber optics and the future patent that you will hold in our field. So I think that it's very commendable, the work that you've been doing. So thank you for sharing these very important findings with us. Are there any questions with this application? I think we look forward to your papers in the future regarding your applications, and I think having the first application on this bridge is also very interesting. Thank you very much. And it seems like the margin of error in your results currently are very, very small. They're very marginal.
Yes, at the beginning we had some problems with the development of the sensor, but nowadays it is working.
It's working very well. Thank you. Thank you. So we can move on to our third presentation, entitled Experimental and Numerical Study During Construction of Multi-Story Buildings Using Clearing or Partial Striking by Professor Alvarado Vargas.
Thank you.
Thank you.
Well, good morning. My name is José Alvarado Vargas. I am a PhD researcher at the Universidad Politécnica de Valencia. This presentation shows an experimental and numerical study during construction of a multi-story building using clearing or partial striking. Improving construction deadlines and costs largely depends on recovering all or part of the components used in the building process as quickly as possible. However, this strict line depends on many things, especially on the system and the construction process we use, on the future of the building work itself, the type of concrete or load designs, and even of the environmental temperature and humidity conditions involved under which the work is performed. Looking to improve construction deadlines and costs in Spain is used a technique known as clearing or partial striking. This technique consists of removing the formwork at 50% of the short that support the slab a few days after pouring the formwork and after pouring them without completely removing the shoring up, thus reducing the material required for the formwork and shoring of the structure. The experimental model consisted in a building with 3 stories of 0.25 meters thick reinforced concrete floor slabs with 6 meter clear span between columns and cantilever of 1.80 meters. The height between floor was 2.75 meters, and the foundation of the building was a 0.14 meters thick reinforced concrete slab. The construction process was based on maintaining the shoring on 2 consecutive stories. You can see in the pictures the construction process. The first step was a casting of level 1, 3 days the clearing of first slab, day 7 casting of second slab, day 13 clearing of second slab, day 14 striking of first slab, day 17 casting of third slab, day 20 clearing of third slab. To simulate 3 consecutive short story, in the 24th day, load similar to the weight of the slab was applied to slab 3. And the last step was the striking of slab 2. There were a total of 80 shorts instrumented. Each of them had 3 strain gauges. You can see the instrumentation process in the pictures. And in the slab 1, all the shorts were instrumented. All the shorts were instrumented in the slab 1. And the slab 2 were instrumented, all the shorts of the primary straining piece, the color red, and only the shorts of 2 secondary straining piece of the discontinued line. The experimental measurements were divided in 2 parts, continuous measurements and periodical measurements. The first one measures the load of every short in each place until it is removed. These show the load variation due to building operation. Building operation, temperature variation, and construction and advanced construction. the periodical measurements only show the due to load building operations. To calibrate the final element model and to know the influence of the building operations, we use the periodical measurements. From the periodical measurements, we obtain that when each slab was being cast, the total load was transmitted to the shores. For example, 100% of the load was assumed by the shore below slab 1, and the same happened when casting the other slabs. After clearing, the 3 slabs supported a high proportion of the load. Slab 1, when clearing slab 1, this one supported a weight equal to 46% of its weight. After clearing slab 2, this slab supported a weight equal to 48% of its weight. And after clearing slab 2, this slab supported a weight equal to 45% of its cell weight. And after applied load on a slab previously clearing, the slab assumed. After casting slab 2, 74% of the load transmitted by the shore was assumed by the slab 1. After casting slab 3, 72% of the load transmitted by the shore was assumed by the slab 1, by the slab 2. And after applied load on slab 3, 78% of the load was assumed by the slab 3. The previous result of experimental study led us to calibrate the final element model. The final element model considered the next hypothesis. The reinforced concrete slabs were assumed to have linear elastic behavior, and variation in their stiffness during the test were considered. Columns were modeled with linear elastic behavior, and variation in their stiffness during the test were considered. The steel shores were considered as elastic elements with finity stiffness supported at the ends. Formwork boards were considered with linear elastic behavior and finite stiffness. Straining pieces were simulated with linear elastic behavior and finite stiffness. The foundation was considered to be infinitely stiff, and creep and shrinkage effects in the concrete and temperature change in the elements were not taken into account. To model the building process, we use ANSYS. Concrete slabs and wooden formworks were modeled by two-dimensional shell 63 elements. Two steel shores were modeled by two one-dimensional lean 10 elements. And concrete columns and steel straining pieces were modeled by beam 44 elements. ANSYS allows to perform an evolving calculation by means of different load steps. A load steps consists of calculating structure with the material geometry and properties corresponding to each of the building phase considered. For example, striking of level 1, clearing of level 1, shoring of level 2, clearing of level 2, and etc. Here we can see a comparison between experimental measurements and final element model results. There is a good fit between both results. The mean of the ratio between experimental and numerical loads is 0.96 with a standard deviation of 0.15. The most significant difference between experimental and numerical results are given in the steps 3 and 4, corresponding to clearing and clearing of level 1 and casting of level 2. These differences are due to an error made when removing the formwork from level 1 in the experimental model. The conclusion we get from this study are: the clearing, parcel striking, reduce the use of shores, formwork boards, and straining pieces with the consequent cost saving for the building work that this entails. A study of the average load on the shores shows that, due to clearing, floor slabs take a load representing an important percentage of their cell weight. The simplified methods normally used for evaluating load on shores during the process of shoring and striking do not enable this reduction to be evaluated. The developed final element model considers the construction process followed in the experimental model, as well as the evolution of the concrete properties during the test. It was thus possible to simulate load transmission between shores and concrete using shoring, clearing, and striking process. The final element model was verified by the experimental results, and it was concluded that the method adopted in the models is suitable for use in actual buildings. We'd like to thank you to Universidad Politécnica Valencia, ICITEC, Ministerio de Educación y Ciencia, Encofrados Alsina, Copasa, Rupolos Casares, and AFARS. Thank you.
Thank you, Alvarado Vargas, for the very enlightening presentation. Are there any questions for our presenter? I think all the presentations are outstanding today. Nobody has any questions. I think your findings will be wonderful for the construction industry, for the companies, for the economic savings that will entail. And it's also nice to see your results with ANSYS, comparing that with the experimental data that you had at the site for that one structure. So the mean and standard deviations are very low, so it's a promising application. So thank you very much. Let's continue with our next presentation. The presentation is entitled Wind Behavior Tests on Lightweight Ventilated Facades by Jaume Avellaneda.
Professor of the Architectural Department of the Catalunya University Technology, and I will present this paper. In our country, the construction of housing building facade has evolved from the conventional system made with brick masonry to the modern light systems made with plates or panels of different materials following the ventilated facade model. The difference of weight between the two systems is important. 250 kilos square meters against 60 kilos square meters. And that implies savings in the cost of the structures and foundation of the buildings, but also in the same facade. The thermal and acoustic behavior of the facade, the light facade, is an issue with very papers, very knowledge. But there is a lack in the behavior of the behavior of this kind of facade in relation to the pressure of the wind and also static and dynamic pressure. This paper intends to establish the behavior of two different systems of lightweight ventilated facade from the wind axioms. The two test methods are the structural stability and deformation by uniform static air pressure difference, and the structural stability and vibrations in a subjective way using wind dynamic pressure. The specimen is a real scale, is a part of a facade of a real scale, and it has 63 centimeters high and 4 meters wide. This represents 2 floors. The pressures used were calculated for the Barcelona region and for a building of 20 stories. In the value of this pressure are considered the gust wind, the important gust wind. Tests and the standards. The static test was carried out by the European rules, EN, and the dynamic pressure was carried out by American rules, because it does not exist in Europe a standard for wind dynamic pressure. Electronic instruments were used to permit the rapid acquisition of data, and also visual instruments. Specimen. There are two kinds of facade. This main structure is the structure of the chamber of the test, and the facade is that. There is inside the structure, the structure of the facade is the same in the two cases. Is the lightweight perfil, a steel perfil, and there is a board, cement board, with airproof membrane, and outside there is the rain screen. The rain screen has his structure in a structure of aluminum. This part is the same in the two cases, but the outside is two different cases. The facade system B and system A. The system B, the vertical member of aluminum, is subjected only in the bottom and in the top of the structure, here and there. And in this case, the aluminum structure of the rain screen is subject with the inside structure, with screws. This is the chamber, the test. The test is static in this case. This is the inside wall of the facade. And this is the dynamic test with engine of airplane with 4 meters of diameter. This is the assembly of the exterior facade, the cladding, is the B, the system B, and the system A. These plates are three-space composite. It's a composite. It's a plastic composite. And in this picture, we can see the situation of the values, the points of the values of the deformation. This is inside the electronic sensors. Inside there are electronics in the member, vertical member, structural member, and in the middle of the panel of concrete, the cement, sorry. And inside there is the visual deformation, the visual sensor is that. That is a pencil. That is a pencil. The pencil is fixed to the main structure of the chamber. Is fixed, always is fixed, and the display with the paper is fixed to the inside the structure. This can move, can deform, and the pencil draw the deformation. These are the deformations in positive static pressure and negative static pressure, two kinds of pressure, suction and pression. And you can see the deformation, 20 millimeters, is bigger than the deformation that the rolls allow. In this case is 13.8 millimeters. In this case, in the last step of load, 2,800 pascals is bigger. And in this case, in the negative pressure and suction, the problem is that it's failure the panel in this step. You can see the failure, the cement panel with suction, pull up of the member, the vertical member, the structure of the facade, and you can see the screw and the kind of the failure. These are the data of the different deformation, and this is interesting because it's the visual sensor. With the visual sensor, we can see the movement. This is the pencil, the point of the pencil. We can see the two movement. The movement in vertical and in horizontal. Why? Because the structure is a U of steel with the pressure, positive or negative, is the same, turns and produce this movement. When the pressure is producing, begin the deformation, and before when the pressure is reduced, the point turn to the same, come back to the same, to the origin. This is the drawings of the break, and this is the visual of the vibration. The vibration, in one case, in the point D, in the point D, the vibration is very, very little, and in the point B is the other facade is 1.25 millimeters, very, very little also. Then, in conclusion, first, the lightweight steel perfiles had deflection higher than the maximum deflection fixed by the rules, in this case 13.8 millimeters. Therefore, it's necessary to increase the dimension of these perfiles, Second, the screws in the union between the cement board and the steel perfiles had a poor behavior. The design of them should be changed in order to prevent this kind of failure. Third, the cladding structure had a very good behavior in relation to the dynamic pressure. And fourth, the facade B had a better behavior than the facade A in relation to the transmission of vibration to inside. Thank you very much.
Thank you, Professor Avellaneda. Do we have any questions for our professor? I think that his findings were very interesting, but also from the policy perspective, it's interesting to see that there are no standards in Europe yet for the wind. So this is something perhaps that's very important that needs to be worked on, because you spoke about the wind gusts in Barcelona, but perhaps all throughout Europe, similar problems. Wind dynamics. Sure. Sure. Yes, it's very important. The American codes. It's similar in Turkey. We also use the American codes because we also do not have these dynamic codes, unfortunately. So thank you very much for your presentation. Our next presentation will be entitled Research and Analysis about Determining Constructive and Project Factors in Domotic Housing by Professor Milan Angles.
Hello? Then the US, the first electrical appliances appeared. They were thought specifically for home usage, and also there were the first devices installed to control comfort, temperature in office buildings. Well, the first who defined the term of domestics was Larousse Encyclopedia in 1988, but clear division hasn't been reached since then. This is the reason why a definition has been made up to set the concept of domotic in the world research. Domotic in the research is this expandable group of services that integrate into the house to a greater or lesser extent that are supplied by systems able to take shape in one of several environment internal networks and able at the same time to communicate with external networks from the house. These services are about functions related to energy saving, technical management of installations, data, communication, leisure, accessibility, assistance, comfort, and so on. And it can be controlled from one or several points on management centers. The same way, series of essential terms have been made up in order to guide the research. We can stand out the following. Integrated domotic installation is, in architecture, this one whose main components perform a double function. Its own function of the offered services domotical and the architectural. The constructive of designing factor is the one which hasn't been taken into account up to now in the draft of phase in the construction phase, and it's necessary to design a domotic installation satisfactorily. Well, in an automated building, we've got inside a data network of the same nature or very similar to computer networks. This is the reason why we are studying the technologies and this discipline that rather usual to the figure of the architect, but necessary to understand and grasp domotic. In the research of constructive factors, there has been included nowadays the study of the main implied of important technologies in domotic. These technologies derive from computer and telecommunication. They have been classified into following types: technologies which define communication protocols, technologies which define controls protocols, and technology which defines platforms or frameworks and middlewares. These technologies have been cataloged in three groups due to the abstraction of the level they live. In other words, the function that the technology develops within the different layers of the network architecture. It's wrong that the layers of the network architecture of three groups of types of technologies isn't accurate or inflexible, but it's a useful tool to categorize the field of action of technologies used in domotic. A building with a domotic installation is a building provided with one or several internal networks with automated a serial of devices. These networks can be connected or not, and external telecommunication networks from the building. This is the reasons why there has been the need in this research to distinguish the constructive or designing factors derived from the possible connection to external networks. An automated house doesn't have to be connected to external network necessary to be considered like such, but this connection to external networks does play an important role in the possibilities of new domotic devices. As regards constructive and design factors detected and analyzed in this case, this has been the main conclusions. Infrastructure ECT, common telecommunication infrastructure, has got strong factors that affect common zones or groups of residential buildings above all. then it's necessary to provide large shelves of room and allocation of specific rooms that require their own technical conditions. We can clearly distinguish between common networks of the building and the user network, which starts also inside the house and is to be planned both the road of the minimum equipment of access intakes and reserve of canalizations. There are either any difficulties in planning from the designing point of view and coordinated with this installation, the room and necessary canalization that will be used lately by specialist workers. This is the graphic of research of 50 houses of domotics in Spain, and the results that I only take three of the gasps. There's no specific regulation of domotic installations in Spain. Nevertheless, there are two national regulations that are about the automatics of housing. On the one hand, there is the ECT, Common Telecommunication Infrastructure Regulations, that regulates the common telecommunications infrastructures for this access to the communication services inside the buildings and the installation of the telecommunication systems. However, the ECT regulations don't talk about necessary infrastructures at home to install domotic systems, being this automation system energy, comfort, and security management in houses and buildings. The systems are regulated by EBT Spain regulations, but these regulations have to set the technical condition and necessary warranty to the system executing automation tasks. Well, the immediate conclusion of this study is the confirmation of the existence of a few constructive and designing factors that the architect has to take into account to develop automated building satisfactorily. Therefore, we have constructive factors detectors in application of the new technologies. The select type of the technology determines the internal network topology of the house, whether if it needs or not specific wiring, or even it sets the relation among devices of boosters. Human-machine interfacing due to define these aspect conditions, but above all qualifies new spaces in the house and didn't exist until now. And factors in automated buildings with connection to external networks. The planning of spaces in the is the most important factor regarding the connection of the internal networks of the house with external networks from the building. Regulations don't define satisfactorily characterize the field of domotics yet, so a revision of the ABT with the ECT will completely determine the warranties that canalization and wiring of related domotic systems must have. Well, then it would be possible a domotic pre-installation, which would depend on a man-intense routing not yet offered by the companies, and which is an important factor because it affects the user's confidence when demanding a domotic installation. Finally, it's been checked that the way integration is taken in domotics has to change, thinking of this as the merge of both service and constructive element. In order to this, it's essential the architect knows the new technologies well. Thank you so much.
Thank you, Professor Angles, in telling us about the challenges that exist for automated buildings. The room is getting very hot, so I have requested from our assistant if we could have the air conditioner turned on and perhaps the door opened. I apologize for the heat in the room. The next presentation, I would like to ask if the authors of a study on different typologies of wind catchers has arrived because they haven't checked in this morning with us. So I will go over to the next presentation, the modifications of the main facade of the Spanish Senate Palace by Alonso de la Calle will be presented next.
Estará en el escritorio.
Well, my name is Monica, and I'm collaborating with the Department of Construction and Technology Architecture Universidad Politécnica de Madrid, and we want to show you our work about the modification of the main facade of the Spanish Senate Palace. As introduction, we should say the Senate Palace is located close to the Royal Palace, and nowadays is one of the most visited buildings in Madrid. It represents the development and the political changes that have been recorded throughout Spanish history in the last 200 years. At the beginning, the current Senate Palace was the Augustine Monastery and School of Doña María de Aragón, built around 1581 by Francisco de Mora. The site was built according to the traditional systems. The church was rectangular in plan, and its front facade had a higher rectangular vertical section with a projecting doorway on the ground floor. This general arrangement has been preserved, and the Senate Palace was fit into the old mold of the school, which the legislative chamber occupies the old church. The transformation of the church into a chamber, the former monastery was turned into a civil building in 1814 by the Navy engineer Antonio Prat. This engineer created the new oval perimeter for the chamber with a filling up of the rubble from the demolitions, and he removed everything that betrayed its former religious nature and replaced them with new civic and patriotic symbols. However, from 1814 to 1820, the monastery was returned to the monks, who demanded the restoration of the spaces and representative construction elements. Who restored its former religious use into legislative chamber was Isidro Velázquez González in the first few months of 1817. Velázquez worked to alter and consolidate Prat's legislative chamber to restore its use as a church seems to have been centered in its back section, which was the most affected. In March, it was necessary for Isidro Velázquez to again alter and refurbish the interior to transform the church into a lay temple. This architect, Isidro Velázquez, had to direct the works required to turn the parish church into the legislative chamber in less than 3 months. With respect to the facade, the same architect had to demolish the recently built towers, but he kept some pilasters without a capital, which supports a Doric entablature, and the pediment of the new temple. During new absolute slabs, the civic building became a monastery again, with the monks taking over between 1824 and 1837. Aníbal Álvarez Buquel was responsible for the alteration of the legislative chamber to exalt Queen Isabella II when she came to the throne. His main contribution to the Senate Palace was the design and construction of its facade overlooking the square. The part of the facade corresponding to the legislative chamber was based on a simple and balanced construction concept, which consisted of a large horizontal rectangle divided by 4 huge pilasters into 3 vertical sections. The central section had a door and a thermal window enclosed by a large arch, and the narrower side sections had a large window at the bottom and a niche for statues at the top. Above the entire rectangle was a large pavement with bas reliefs and groups of sculpture. The rest of Alvarez's facade for the former monastery section was more conventional. Large scale works were undertaken between 1882 and 1883, designed by the preservation architect Emilio Rodriguez Ayuso, such as the English Gothic style library preserved up to now as originally built, which occupies the monastery's first cloister. However, as far as the facades are concerned, our interest in Rodriguez Ayuso lies in his design to alter the main facade for the monastery section, as he did not touch the legislative chamber front by Alvarez Buquel. In the end, this design for a new facade was not implemented, as it was not approved by the Fine Arts Academy of San Fernando. When Ayuso died, Agustín Ortiz de Villajo took over the Senate works. His intervention was limited to transforming the facade of the old school sections, whilst keeping the Isabelline one by Alvarez Buquel for the legislative chamber. This work concluded an important part of the Senate building's architectural history until its new state as the National Council between 1940 and 1975, and the Spanish Senate again since 1977. After the Spanish Civil War, the architect Manuel Ambrose Escanellas was appointed as the preservation architect of the National Council building. As the building had been on the war's front line, it was abandoned for the 3 years the war lasted. According to the report written by the architect himself, the first work carried out in 1939 and 1940 was to repair the damage caused by the impact of cells in the wooden section supporting the dome, filling in missing roofs and skylights, and rendering all the facades. The mentioned document states that very important works took place in 1950 and 1951, as the entire main and the sides facade were transformed. We can see on the image the evolution of the facade during these works, with fill voids, openings, eliminated elements, added elements, and replaced elements. This is the state of the facade after this work in 1950. New paragraphs in the report by the architect contain data on the enlargement of the Senate place with the construction of the second story in the main facade in 1969 and 1974. This is the state of the facade nowadays. This report states that artificial stone panels, bats and polished arcosite were used from the second floor to the roof, and natural stone panels from the pavement to the second floor within white columnar limestone and past and lintels. However, only the base cores and column bases are made of granite. Taking above into account, as well as the studies conducted, we believe that the implementation phases of the south facade may have been following. First of all, prior repair of the facade with the demolition of all unsafe parts. The second one was covering the existing wall with hollow brick to obtain a continuous plane for the new cladding. Then placement of the blocks in rows, leaving a cavity with the maximum thickness of 4 centimeters, which was filled with very compacted gray cement mortar. According to the samples obtained in the characterization style. And finally, filling the cavity with mortar, inserting the corner anchoring elements in the base. As conclusions, the architectural and construction development of the main facade of the Senate Palace was not only due to the building's functional requirements, but above all to the architectural trends of the time, as well as the building's historical background. Right from the start, the fact that it was based on a monastic building dominated by this church has conditioned the dual nature of the structure of the facade, the legislative chamber, and the rest with the former church becoming the chamber, and the old monastery the administrative section. On the other hand, the arrangement of the openings and the types, the presence of or not of colonnades entrance, were altered to reflect the architectural style of the age rather than to respond to current use or stability requirements. And lastly, the construction of the Korean facade betrays that it was completed at a time of financial shortage since hardly any fine materials were used and were instead replaced by prefabricated Portland white cement elements. We must say also that it was typical of that time to mitigate the lack of financial resources by adopting the Portland solution, Portlandista. However, currently used and maintained, it still looks quite good with hardly any defects, and it has managed to survive to this day with most of its dignity intact. So thanks.
Thank you, Monica, for sharing with us
Well, I'm so sorry.
what happened with the Spanish Senate building from the 1800s till today. It was very interesting. Are there any questions for our speaker? I would like to ask if there is anybody that will present the seismic analysis of masonry infilled reinforced concrete frame structures talk. I think they have not checked in with us. And the next presentation, installation of security and protection of residents against violent intrusion. Okay. Can I also ask if there's anyone to present the urban sewage solutions in case of cloudburst? Okay. We've had 7 presenters, which is a great number. We'll have a little extra time before lunch, I think, after our presentation.
My name is Javier Balbás. I go to speak about installation of security and protection of residents. The European Union has had an important increase of members. In the 2006 Europol reports that organized groups move in all the European Union, which possibility movement of capital and arts it exists criminal anonymity. Also, the significance of the international economical crisis is the organized crime. Now, the type of robber is violent, fast, and destructive. In addition, the offender is prepared and is very violent. More knowledge in electronic device also is know the events of Moreno and the crime of a married in Novelda, Alicante, Spain. So it's very important the security inside and outside home. A security system is composed for an equipment detection, the purpose of action, a user protection. For equipment detection and purpose of action, exists the perimeter control plus alarm. And for use protection, I go to present a penny room. The perimeter control is a power line which detects a power cut. At the lot of picture, there are two detector lamps. Exists an equipment integrated in construction, detector lamps, and barriers for doors and windows. The economical valuation versus others technology is favorable for infrared barriers with a strip lamp. In regards alarms, is necessary an electronic central for to connect perimeter alarms. One possibility is Simon Box 2. It has possibility of 4 messages to different mobile, action sirens, alarms, and a warning power cut. In this moment, its inhabitants are or alert. When inhabitants are at home, it's very efficient, the panic room. The panic room is integrated into the house construction, and the best room for the panic room is the bedroom. In the picture, it's in the bedroom, or a room, the center of house. In the graph, panic room cost versus the size. For a panic room that has armored walls and a door and considering the square surface. In the picture, a panic room of 20 meters square costs approximately 55,000 euros. It's very important that people doesn't know of the panic room, only inhabitants. In the picture, there are a panic room hidden and armored windows hidden and armored doors hidden. For cleaning, nurses, etc. Don't know on the panic room. In regards to the wall, they are to ensure resistance, impacts, fire, etc. In the picture, there is one photo on a wall, armored or wall. In regard to the door, on a wobbler on the look, which is tiny pins in radial position for to put up impact continue. Once in the panic room, you have to install cameras hidden for to know where the thieves. Also, avoid telephone for to prevent the inhibitor of frequency. Also, you have to install an autonomous energy system. Two is very important, separate and protect ventilation system for the possibility of fumes. And finally, a security cabinet of emergency with a oxygen cylinder, as possible a hole in the wall, as ventilation, as fumes. As conclusions, first, there has been an effective security system. A security system as an attractive decoration object. Also, is integrated construction. It's possible to perform a facade construction as economic benefit, and with ability to be a part of modular construction. In the book of Congress is my email for question about panic room. Thanks.
Thank you, Mr. Garcia. Are there any questions for our speaker? We usually don't think about panic rooms and preparations for emergencies like this. We usually think about how to evacuate when there's a fire or an earthquake. So it's interesting to hear the architectural needs if there's a thief in the house and how we can protect our loved ones. So thank you very much for your presentation. I was told that we have the speaker for the final paper, Urban Sewerage Solutions in Case of Cloudburst. Professor Aranda will be presenting our 8th paper.
Good afternoon. My name is Jose Aranda. I am civil engineer and university professor. Our work is titled Urban Sewerage Solution in Case of Cloudburst Downpour. Urban Sewerage System summary. Improvement of the maintenance system of the sewerage system. High air system, clean line deposit. Intermediate air downpour rolling storm deposit. Low area, urban center, left of flow with the extraordinary downpour of 50 years, strong tank. do not weep below water line in the rain for a return period de 500 years. Sunny day. Section the street is a mountain. This photo is Calvo Sotelo Street, Santander, Spain. Section the street is a V, Roman Road. This photo is León, Spain. No problem. The rain day, many problems. Photo 1, Santa Fe, Venezuela, a flooded valley, May 2010. Photo 2, Arriondas, Asturias, Spain, a flooded valley in June 2010. Barcelona, flood the metro station, Sants. República Dominicana, urban center. This photo, a woman, a girl, Abu Dhabi, July 2010. Y Spain, Treseño, urban center. The design, Silvers, three house liters per capita per day. Strong water. In Spain, technical building costs. Calculation, isoyetas, map, return period 20 years. My hair value must 3 houses times service. The commercial software, la design condition, housing a look type, 300 liters per capita per day, suppose 0.044 liters per second housing. Runoff road 0.95, green area 0.5, return period 10 years. Maximum early rainfall 50 millimeters and time. Topography, unlocked areas and steep. The construction single house, deposit clean con automatic discard. Design siphon hydraulic clutch is hard to the part a clean pipe. Retention of rainwater system. House, single house. Minimum volume of the clean deposit system 500 liters. This solution, the Arab call the system aljibe. Y foto tradicional. This volumen, volumen Paul, this 25 cubic meter. Housing developed in construction, surface 2 hectares in construction. Minimum volume control for building 48 cubic meter. Dimension deposit 60 and 2 and depth 1.5 meter. Deposit clean deposit 3 cubic meter dimension. And other solution, 2 pipe of 30 centimeter diameter and 20 meter the long. Sewer system, the sewer pit the pip sewers and rains water in the same draft 40% of diameter. Hydraulic close, no small. Low areas, green areas, parks, urban center, deposit 5,000. This one. City hall, strong tank, sample. Capacity 5 to 40 cubic meter per hectare. Real cash, Pozuelo de Alarcón, en Madrid, Spain. Other solution mejor. Tokyo server system. This example to avoid the flooding. Scaling solution, house, single house, housing developed in urban center. No to building in flow areas. In conclusion, the necessity of prevent in design, rainfall intensity and return period 50 years. Required to pull local collection system and rain water will hydraulic close on an automatic disrepair. Security, the construction of house got a spillway for a return period of 500 years. And a strong tank in green areas and parking. Reuse of rain water for irrigation. gratitud en cuestión al señor Carlos Díaz Cerveta, y de cuestión you can send your question and comment to email. That's it.
Thank you, Professor Aranda, for your enlightening speech regarding urban sewage solutions and important lifelines. And we've noticed that for many natural events that occurred, you showed us a lot of flooding problems,
Sí.
that mitigation and preparedness for these floodings is very important. So thank you very much. Are there any questions for our speaker? I think everybody's tired and ready for lunch. So thank you for your participation, and thank you to the speakers for their outstanding talks.